Welcome to Python for Machine Learning, an online training brought to you by the Vlaams Supercomputer Centrum. This is a QR code that links to a small website, and you can find some information about this training there. You also find a link to a GitHub repository that contains all the material for this training, including the slides which we're watching now, and source code, some Jupyter notebooks, some data in order to follow along. Feel free to clone the repository or fork it if you like. So, it's pretty obvious if you follow the media that machine learning is making really big strides at the moment. This is due to a number of factors. In my opinion, the most important one is that we now have large and good quality data sets. Think of Google, think of Facebook. They all have a lot of information, and a lot of information that we actually tagged for them. Consider Google Photos. Many of us add tags that describe the photo in some way, for instance the subject, or location information, and so on. So this makes for very good training sets, and they were produced pretty cheaply in the sense that we did it for Google. Another factor which is also quite important is the increase in available compute power, especially with the advent of graphical processing units, so GPUs. Compute power has increased dramatically, and that of course has quite an impact on what you can actually do with respect to algorithms, how sophisticated the models can be that you're trying to train. And of course there is also progress in algorithms. Although fundamentally they're not that different from, say, 20 years ago, still there are some very interesting tweaks which make current algorithms much more interesting and much better suited to tackle current problems. There are many interesting applications, of course commercial applications, which you're already familiar with. For instance, think of assistant technology such as Amazon's Alexa or Google. But also scientific applications are quite interesting. And of course there is a link with artificial intelligence, obviously. However, artificial intelligence is not machine learning. There are different things. So, in machine learning tasks, we have several which are of interest. For instance, we've got supervised learning. So that would be your typical regression problem, predict numerical values from some data set. Also classification. That means we try to predict categorical values, for instance labels of pictures or something like that. There's also unsupervised learning. That's actually a bit harder because we don't have questions and answers, we don't have labeled data. So the information needs to be determined from the structure of the data itself, which is a lot harder. One of the most prominent techniques is the clustering. So trying to group your data set according to some distance measure. And of course, that's where the interesting thing is. What is this distance? How do you define that meaningfully for your problem, for your data set? Another typical application is association mining. Find frequent co-occurrences. Think of your typical shopping cart in a supermarket or online shops such as Amazon. If a certain customer buys product X and Y, probably he'll also be interested in product Z. So let's suggest that particular product to him. And then there is link prediction, discovering relationships in data. And one application you might think of is Facebook, which suggests that you might want to be friends with certain people. And that is just based on discovering relationships between you and other people, and those other people again with other people. So basically you try to predict a link, a potential link between different individuals. Data reduction is also sometimes classified as unsupervised learning, or it may also be considered a category by itself, depending on who you're talking to. So what you're trying to do in data reduction is project features in a very high dimensional space, 10-dimensional, 20-dimensional, 100-dimensional, to a much lower dimension, 2 or 3. And you might want to do that in order to visualize high-dimensional data, or to try and find the structure in that high-dimensional data. Of course, our intuition about higher dimensions, it is higher than 3, is actually quite bad. We don't have gut feeling for that, and it's very easy to make pretty trivial mistakes. And another very important category is reinforcement learning. So that is, for instance, a self-driving car. So let's look a little bit into regression and some applications of that. So a very nice one is colorize black and white images. You see quite a number of examples. So the input is essentially a grayscale image, and the output is that same image but now colored. So if you have a training set, and that's kind of easy to make, you just start out with color images and you reduce them to grayscale. That would give you a nice training set. You can see that results are actually quite promising. Many of the pictures are looking quite natural. An example of classification, so the second major task in supervised learning would be, for instance, object recognition. So here you see multiple objects detected in the same picture. For instance, you see that the red rectangle is classified as a dog, the greenish rectangle is a hat with a brim. So basically, as you can see, the detection of different categories, of different classes, can actually be quite sophisticated, and Google is doing a rather good job on this. Reinforcement learning, that's actually learning to do by doing. So it's learning from experience. Basically, you start out with something that has a very bad performance, but you keep on letting it play. And if it does well, it gets rewards. If it does badly, it gets kind of punished. And so basically you try to maximize, or the algorithm tries to maximize the rewards, and over time gets better. A nice example is learning how to play Pong or Breakout. So basically the paddle has to be used in order to make the ball break the bricks, and after a relatively short time this algorithm is actually playing almost perfectly. So that's a very nice task. Clustering, this is also an interesting example from India. The Department of Justice was trying to determine crime hotspots, and of course the idea is to either have more police patrols or to try and deal with crime in a different way. And so this is an example of using k-means clustering. So they use the database of crimes and try to cluster them according to geographical location. There are also, as I mentioned, applications in science. For instance, for Earth observation, for instance, you might want to classify land usage. There are also quite some applications in biology, in bioinformatics, and also in medicine. And even in, let's say, the hard sciences, such as material science and so on, quite some interesting progress has been made. So what we'll be discussing here, we will talk about regression. And of course there are many regression algorithms. For instance, rich regression, support vector machines are quite popular. Random forest is very popular. Neural networks, either the classic multi-layer networks or deep neural networks. So for classification, we have, for instance, naive Bayes, again support vector machines and random forest and neural networks. So we will be talking about rich regression for regression, naive Bayes for classification, and we'll also discuss deep neural networks a bit. And along the way, of course, we'll also talk about multi-layer neural networks, since you need to understand those in order to understand deep learning. And for clustering, we'll talk about k-means. And again, there are other algorithms, such as, for instance, hierarchical clustering and so on. Of course, machine learning and AI have their issues. So one of the major issues from our point of view is that many machine learning projects or AI projects actually fail. And Gartner claims that that would be 85%. We'll discuss why that actually is the case. And of course, there is also an ethic point of view. For instance, Amazon has had to close down a program by which they just automatically fired employees that were not performing according to whatever criteria they had, and that was done by an AI. No human intervention, they just got sent an email, goodbye, thanks for your support. So basically that was ethically not acceptable, and they had to close down that program. There are many ethical issues, and of course it's an active area of research. So let's talk a little bit about failure. So why do projects fail? One reason is asking the wrong question. So before embarking on some machine learning project, you should really get your questions right. What is the question which you're trying to answer? Is that what the client, which might be you, is actually expecting? Or are you trying to solve a problem that no one's interested in? So one of the other issues is that you don't have enough data. Many people attempt to do deep learning on very small data sets, which means that you're trying to estimate a huge number of parameters from a very small number of examples, and that is likely to fail. One of the things which you may do in order to alleviate this is use transfer learning. And of course you might not have the right data, so if you're trying to find an effect which is not represented in your data, then obviously you're not going to find it. Having too much data is another issue. You might be deluged in data, and it just contains too many features, and you're not able to distill the actual information which you require. And of course you might not have access to the right type of people. Finding profiles to do data science, to do machine learning, is not that easy. And of course you might be using the wrong tools, but that's why you're here. We'll show you some nice tools to use for data science and deep learning and machine learning projects. And then of course the model which you use is quite important. If you use the wrong model, you probably are going to get bad results, and that is not easy. That requires some gut feeling which you can only develop over some period of time through experience and through failure, essentially. And then of course you have to be sure that you measure performance the right way. So your algorithm might be doing okay, you think, because actually what you're trying to use as a testing set is not really corresponding to what's out there in the real world, and then when you deploy your model into production, it suddenly fails horribly because the real world data contains some cases which were absolutely not represented in your training and testing data. So again, that would lead to a failure. So we will be talking about frameworks, and of course if you think about machine learning, then Python comes to mind very easily. But of course there's also R, and some people are still doing machine learning directly in C++. We'll be discussing Python here. And for doing machine learning, there are lots of libraries. One of them, which is a classic, is scikit-learn. It has been along for quite a while, and it is quite popular. It has a lot of algorithms. PyTorch is quite interesting as well. It's developed by Facebook, while TensorFlow, which is extremely popular, is developed by Google. And then there is Keras, which is essentially more high level and which can use TensorFlow under the hood. So you get little code that relies on a very performant underlying framework, which is TensorFlow, which might be a very good combination. So scikit-learn is classic machine learning, but we'll see that it can also do some interesting things in other kinds of projects as well. While PyTorch, TensorFlow and Keras are all concerned with deep learning. Here we'll talk about scikit-learn and a little bit about Keras as well. However, you have to realize that this is a very fast evolving ecosystem. So basically the libraries which we're using today might not be those which we use tomorrow. However, underlying principles of course remain the same. So what you learn today will be useful tomorrow anyway. A very important part of any data science project, and machine learning in particular, is to have a proper data pipeline. So that starts with data ingestion. Where is your data coming from? It might be CSV, it might be semi-structures such as JSON, XML, or it might be HDF5 files, it might be images, it could be data from a relational database or a NoSQL database, it might be scraped from the web, whatever. One of the things which you can use is Pandas, which is a very nice framework that allows you to deal with data that can be thought of as stored in tables. Data cleaning is typically the next step after you've ingested your data. Do you have outliers? Are there any invalid values? So if that's the case, you may want to filter for those so that you don't skew your machine learning training or testing with those outliers. However, if you do so, also do the same thing in production. Do you have missing values? And if so, you have to deal with them. You can just drop the data concerned, or you can impute missing values, basically replacing them by something that may or may not make sense. We'll talk about dealing with missing values later on. Then there is data transformation. For instance, you might want to scale your data, you might to normalize it. So we'll also discuss that. It's a pretty important step and has a serious impact on the performance of your machine learning algorithms. And to do data pipelines, actually scikit-learn is a very nice toolbox. And we'll give some examples of how you do a data pipeline in scikit-learn in a systematic way. And the point is, it must be done systematically. If you don't have a systematic data pipeline, actually your project is quite likely to fail. So, when we do supervised learning, what's the methodology? First, of course, we have our data pipeline, but now we have our training data. So you start by selecting a model. For instance, random forest, a neural network, a deep neural network, whatever. Then you train your model. So that means you determine the model parameters. The data, we're in supervised learning, consists of input and output. That data you would separate into two parts. The training data, that would determine your model parameters, and validation data, that's your yardstick in order to avoid overfitting. So what is overfitting? Consider the plots which you see on the right hand side of the slide. So we've got the dots and we've got the crosses. Those represent two different categories and we want to separate them. The left plot shows you a very sophisticated surface that separates the two groups of data. And you can probably guess that this is overfitted. Because if I would have a new data point, which is not part of my training set, it's quite likely that it would actually be on the wrong side of the curve, since that is way too detailed. On the other hand, if you look at the graph on the right hand side, you see that that is probably also wrong, because the way of separating the two groups of data is just too simplistic. It's a straight line, and if you look at the data, it's quite clear that it is not really the most appropriate model. The optimum would lie somewhere in between. And of course, that would mean that there are some errors. Some crosses will be labeled as dots, and some dots will be labeled as crosses. But overall, it's a very good compromise between overfitting and underfitting, since it will deal best with data that you haven't seen yet, and that is of course similar as what you started with. However, if you have a data set, you split it into two parts, but to test your model. So you set aside training data, and that, as we mentioned, you split into training data and validation data, but you also have test data, and that is used to test your model, and that should not ever be touched during training. So that's data that is used after your training was done completely. So again, that would be input and output, and that is for the final scoring of the model. This is very important. Training data and test data should definitely be separate. And then in production, then you have input and you try to predict the output. And hopefully your training data, your test data, will be representative for your production data. If not, your project fails. So there is an experiment which you can do to play a little bit with underfitting and overfitting, and you see the name of the Jupyter Notebook in which you can do that. You find that Jupyter Notebook in the GitHub repository, which I mentioned at the beginning of this training session. Next, we'll talk about scikit-learn and see how to implement the scenario for supervised learning in scikit-learn with data ingestion pipeline and so on.